So let's see how this works. So we have a collision. The momentum we have seen, this combination of m of the blue ball times its velocity plus m of the red ball times its velocity, we've seen that's conserved in the collision. So the top, the numerator here, the total momentum is a constant of the motion. The bottom, if I just choose to divide by the total mass, that's not changing either. And so therefore this quantity of all the momentum divided by all the mass can't be changing during the collision. Seems straight ahead. So it is this quantity that I'm going to identify. The motion of this quantity corresponds to the motion of that red dot, and we're now going to see how to fix the precise position of it. So this thing is a momentum that has dimensions of mass times velocity, and we have a mass at the bottom. The ratio of those two quantities is a velocity, and it is in fact what I'm going to label the velocity of the center of mass. So velocity being the derivative of the position with respect to time, and the mass just hanging around and being constants here, do you agree that I have done no harm in pulling the derivative outside of that fraction? That's the same as if I were to say ma dxa dt plus mb dxb dt over the sum of the masses. Are we good with that? May I have an amen? Amen. Okay. So that quantity inside the parentheses tells me where the position of the center of mass is. I'm working at the moment in just one dimension. I have this collision happening in one dimension. And it says I should take, well, how to think about that? I should take, this is not momentum at the top now. It is mass times position. And I add that up for the two particles, and then I can divide by the sum, or the total mass. And that tells me how to find the center of mass. There's another way I just algebraically reshuffle this. Do you agree that's the same? Do you agree that this fraction is the same as that sum? May I have an amen? Amen. All right. Thank you, ladies and gentlemen of the congregation. So, but this one makes me think about it in a slightly different way. How would you describe what we're doing in the last expression? So what are those, yeah, way in the cheap seats. A weighted average where the weight is the mass fraction? Is that all right? How many of you have worried about weighted sums or weighted averages before? How many of you have not worried about weighted averages before? Yeah. So what's a weighted average? Well, if you do a normal average, you're adding up a bunch of junk and dividing by the number of junk, right? In a weighted average, this is saying if you have more mass, this is the mass fraction of ball A. If it's bigger than 50%, then you should pay more attention to the position of A when you're calculating the center of mass, right? If I had let's say this one's a bowling ball and that's a ping pong ball. Where's the center of mass going to be? Pretty much at the bowling ball, because there's almost no mass in the ping pong ball. And so this is saying take the weighted sum of the positions of the particles, where the weight factor is the fraction of all the mass that is in that particular particle. Does that make sense to people? Too bad. I mean, okay, good. So I'm going to now make up a name for this weighted sum on the top. And if you did weighted averages before and you took some stats, you might know about moments. How many of you have seen moments? Nah, forget about that. All right, so it's just a definition. If I'm going to take a weighted sum of positions, the positions here xi, multiplied by the weight factor, which is m sub I. That's called a moment. And it's called the first moment because the power, the exponent of x sub I, the thing that I'm weighting, is 1. So I didn't write it. Want to guess if there's such a thing as a second moment? No, definitely we don't want to guess. And that would be with x sub I squared. What about a 0th moment? What would that correspond to, the 0th moment? That would be, in fact, what's on the bottom. So to find the position of the center of mass, we take the first moment of the mass, and then we divide by the 0th moment of the mass.